Evolutionary endpoints of stars. White dwarf, neutron star, and black holes are compact objects that are created when the cores of massive stars during supernova explosions. They are evolutionary endpoints of stars. Where a star ends up at the end of its life depends on the mass it was born with. The stars that eventually become neutron stars are thought to start out with about 8 to 20 to 30 times the mass of our Sun. These numbers are probably going to change as supernova simulations become more precise, but it appears that for initial masses much less than 8 solar masses, the star becomes a white dwarf, whereas for initial masses a lot higher than 20 to 30 solar masses, you get a black hole instead. Now let's look at the physical mechanisms responsible for the formation of compact stellar objects. Stars are born in gaseous nebulae, in which clouds of hydrogen coalesce, becoming highly compressed and heated through the gravitational interaction. At a temperature of about 107 kelvins, a nuclear reaction begins converting hydrogen into the next heavier element, helium, and releasing a large quantity of electromagnetic energy, light. As the star condenses and compacts, it heats up even further, burning the last of its hydrogen and causing the star's outer layers to expand outward. The star then becomes a large red giant. Red giants are hot enough to 108 kelvins to initiate nuclear fusion of helium into other heavier elements. So far, the star is held in near equilibrium by the countervailing forces of gravity, which compresses the star, and pressure from the vast electromagnetic energy produced during nuclear fusion. However, as the star burns hotter and ignites heavier elements that accumulate in the core, electromagnetic pressure becomes less and less effective against gravitation. Without electromagnetic energy to hold the core up, one would think that the core would become unstable and begin to collapse inside. A neutron star is one end for such collapse in a star. When the core of the star collapses, it crushes together every proton with a corresponding electron, turning each electron-proton pair into a neutron. The neutrinos escape after scattering a bit and helping the supernova to happen, and the neutrons settle down to become a neutron star, with neutron degeneracy managing to oppose gravity and thereby stopping further collapsing. This is where the neutron star gets its name. A neutron star is about 10 kilometers in diameter, and its mass is about 1.4 times over that of our Sun. This makes the neutron star so dense that 1 teaspoonful of this matter would weigh about 1 billion tons on Earth. White dwarfs are thought to be the final evolutionary state of all stars whose mass is not high enough to become a neutron star. A white dwarf's mass is comparable to that of the Sun, and its volume is comparable to that of the Earth. After the red giant phase, the low or medium mass star is not very stable and loses mass. This continues until the star finally blows its outer layer off in a gust of superwind. The core of the star, however, remains intact and becomes exposed to the outside universe. This leaves behind a white dwarf surrounded by an expanding shell of gas in an object known as planetary nebula. A white dwarf is very hot when it is formed, but since it has no source of energy, it will gradually radiate away its energy and cool down. Over a very long time, a white dwarf will cool to temperatures at which it will no longer emit significant heat or light and will become a cold black dwarf. However, because the universe's oldest stars are only 10 billion to 20 billion years old, there are no known black dwarfs yet. Another final result of a supernova explosion is a black hole, which is the evolutionary endpoint of stars at least 10 to 15 times as massive as the Sun. Black holes are even smaller, yet denser than neutron stars, compacting 3 times or more the mass of the Sun into a city-sized range. The gravitational field of a black hole is so strong that if the body is large enough, nothing, including electromagnetic radiation, can escape from its vicinity. The body is surrounded by a spherical boundary called a horizon, through which light can enter but can't escape. It therefore appears totally black, thus appropriately gaining the name black hole.